Hello and welcome to my video lesson 4.3 on reflection and refraction. Refraction has Snell's law. So light obeys regular reflection of wave rules, meaning angle in is equal to the angle out, or angle incident is equal to angle of reflection. And that's if you compare it to the normal line from a surface. So right here, this angle and this angle, they must be equal to each other. Okay, this is, I think for most people, pretty obvious. This is a pretty simple concept. When it is a straight barrier or a straight mirror, but if it's reflecting off of something bouncy, you have to draw your normal line from wherever it happens to be hitting. So if the ray comes into this way, well, the normal line is actually this way, so it's actually just going to bounce almost straight back, because the normal line is whatever is perpendicular to the surface, 90 degrees to the surface. So as long as you keep that in mind, then this is actually a pretty straightforward rule. So that's reflection, which is pretty straightforward. But what about refraction? Refraction, it happens whenever light is bending, when it changes from one medium to another. So a common example of this is light bending when it hits glass, okay, or when it hits water. And water is kind of going to be the main one we're going to look at here. So looking at the water here, we can see that in air, this comes down, and glass is very similar to air. So there's not much of a refraction going on at this step. But at this step, between the water and the air, there's a big difference on the refraction side. So you can see that the light bends, and we know the straw is actually over here, right? We know the straw is over here going into the corner of the cup, but it looks like it's on the right-hand side of that. So when you look at water from air, you see the object, but it isn't where you expect. So common example of this would be spearfishing, although none of us actually go spearfishing. Maybe you do, in which case, good for you. That'd be cool. I want to try it. That'd be cool. But spearfishing, when you're looking at the water's edge, you're a little person here with their spear. Okay? When you're looking at the water's edge, you can see a little fishy down there. And you are looking at it, and you see a fish, and it looks like the fish is right there. But that's not where the fish actually is, because the water has bent the light. So you're actually going to have to aim not where you see the fish, but where the fish actually is. Okay? So how can we look at that, and how can we calculate the difference? Well, that's going to be Snell's law. But let's keep talking about this first before we talk about calculations. Another odd thing about light between mediums is if you go from a higher index to a lower index of refraction, you can get total internal reflection. And this is really cool. It's a really cool effect that you can see from the bottom of a swimming pool. So here we're underneath the water, and this is where the person actually is, but you can see the reflection of the person up top. And if you look carefully up here, you might be able to see out of the water, because up here our angle is closer to 90, and so it's not internal reflection. But over here, because the angle is past the critical angle, therefore it is internal reflection. So right here, somehow, this is the boundary between where it's internal reflection and where it's not. This is what we call the critical angle. And so you should look up at the surface of the water sometime and see if you can see this happening. You have to have goggles on probably, but it's pretty cool. So this idea of total internal reflection is really important because we use this in fiber optics. This is just a diagram of what a fiber optic cable would look like. Basically, down here is the core, and the core is just some sort of glass, usually. which is why it's pretty dangerous to be playing with this unless you know what you're doing. And so, yeah, so this glass here can actually break. So these cables can't bend very much. But basically, all the light will bounce inside, back and forth, all the way through the wire to the other side. Just bouncing back and forth. If you want to see this happening, then the cheapest way, residentially, like with what you can buy, is a Toslink cable. Toslink is optical audio. It's a little bit of an older standard now because HDMI has become very popular and honestly quite good. But Toslink was the best standard for a number of years, and it still has some unique benefits over HDMI. Any other copper cable will send signals and have some amount of interference with the ground, with whatever else, when it's sending the signal from one device to another. Toslink has no copper connection. Toslink only has an optical connection. So if you plug in one side into your device, maybe that's your Xbox. I don't know if the newest Xboxes have this, probably not. But the Xbox One, the original Xbox One definitely did. PlayStation 2s had it. A lot of other devices have it. But anyways, so if you plug that one side into your device, this other side goes into the TV. But let's pretend we don't plug that into the TV. You look here, you're going to see a little red dot. It's actually shining a light. You're going to see the light coming out of this end, and you can actually shine it like a flashlight. And that's because it's sending the signal through using light, pulsing light. Okay, so all that's interesting. Total internal reflection, index of refraction, going from, it always has to be from a higher index to a lower index if you're doing that. So generally speaking, let's just talk about some generic rules. Speed, if the speed of light decreases when you're going from one medium to the next, then it must be bending towards the normal. Okay, so and the wave must be faster in medium 1. That's why it's decreasing when it goes to medium 2. The index of refraction of 1 is less than 2. So this is a higher index, and this is a lower index. This is faster. This is slower. Okay, so the angle decreases, meaning this angle in here is less than the angle in. The opposite is true as well. If the speed increases, it bends away from normal. And the wave is slower in medium 1, and index of 1 is greater than 2. So this has a higher index this time because it's the opposite. It's slower. This is a lower index, and it's faster. Okay, so this would be like going from air to, I'll just do water. Air to water. Okay, and this would be from water to air. Okay, so let's consider what this actually looks like if we have different surfaces. Let's have air up here and water down here. Why is it bending one way or the other? Well, if you can imagine you're pulsing light in waves, in rows, okay? So the light is going to go like this in pulses towards the surface. Okay, so let's just consider that. I'm going to try to draw the light here. Okay, actually I'm just going to use the same color. So this. Maybe I should just draw 3, hey? It'll get too much if I draw 4. Okay, so because it's moving faster in air and slower down here, if you watch each of the light rays, when it reaches the water, that light ray is slowing down. So it starts to bend towards the normal. And the other light ray keeps going straight over here and catches up towards that. So it will look like this, because it's being pushed down. It's slowing down on the side that's closer to the normal. So it's going to bend that way. Okay, the reverse is also true. Let's try to continue this, but go in the opposite direction. So if we have it coming up this way, 1, 2, 3, 1, 2, 3, 1, 2, 3, 2, 3, 1, 2, 3. You can see that that first one touches first, but then it speeds up. So it starts to go in this direction. And when this other one goes, there's no room for it, so it'll speed up this way as well. Okay, wasn't super perfect, but you can see here that because one side hits first, it's going to speed up and bend around the corner. This is very similar. My comparison to this is if you have a car, car's tires. Okay, the whole car is still moving at the same speed, but when it hits, let's say mud, and one side slows down, okay, so if this is like a road, okay, and this is like mud, the car tires are going to slow down when it hits the mud, and it's going to be pulled in this direction. Or snow. This will happen the same way with snow. Okay, but if you do it in reverse, and you go from snow to concrete, whatever, road, okay, the same thing will happen here as well. So here, if you're coming in at this angle here with our two different tires, when it hits the road, it's going to speed up and it's going to pull it this way. Because this tire will hit first and get grip, and so it's going to pull this way. And this tire is being slowed down from this part still. So the car is going to get pulled in this direction until it leaves the road snow barrier, and then it will go straight. So just imagine two tires on a car. How would they bend if you're going slower and faster in different areas? That's the same way that light kind of travels. So the refraction, whether you're going faster to slower or slower to faster, follows Snell's law. Snell's law is shown below here, but it's basically, I just want to point out that the index of refraction is the reciprocal of the rest of them, i.e. this one has a 2 on top and a 1 on the bottom. The rest of these have a 1 on top and a 2 on the bottom. So just a heads up with that. But it's interesting to know that the ratio of the angle, sine of the angles, the ratio of the speeds, the ratio of the wavelengths, and the ratio of the index of refraction are all equal to each other. Speaking of, here are now 2 questions based off of Snell's law. Please go ahead and try this out, pause the video, and see if you get the same answer I do. Okay, so here a ray of light with this wavelength enters a glass from air. Air's index of refraction, by the way, is in your formula sheet, so you should know that and find it from there. But anyways, we're going to have N2 over N1 equals lambda 1 over lambda 2. What are we looking for? We're looking for the new wavelength, so i.e. lambda 2 is what we're looking for. So it's going to be lambda 2 equals N1 times lambda 1 over N2. Okay, you plug that into your calculator and you get a value of 333.33333, repeating nanometers. And since we have 3 sig digs everywhere, that's what we're going to end with. So the new wavelength of the light in glass is going to be 333 nanometers. Okay, let's try the second one. The second one says, what is the critical angle of light when you are underwater looking up at the surface between the water and the air? Okay, the index of refraction is 133 of water, and the air you can look up. So again, the air is 1.00. Now, if we're looking underwater to the surface, we have to go in that direction. We always have to go from a higher index to a lower index with air. It always has to be water to air. Okay, higher to lower, in order to have a internal reflection occurring. So to find the critical angle, well, critical angle means we're talking about the 90-degree angle, because when sine is 90, that means if you look at the surface angle in, okay, so if this is our angle in, okay, for water, and this is air, if the angle is 90, well, if this is our angle 2 and it's 90, then our ray is going along the surface of the water. And so at that point, instead of being along the surface, which it can do, it'll start to reflect, well, it'll start to obey the laws of reflection and hop over here. So that's what we're looking for. That when that angle becomes 90. So sine angle 1 over sine angle 2 equals n2 over n1. What are we looking for specifically? We're looking for the critical angle, so we're looking for the angle 1 is what we're looking for. So theta 1 equals sine negative 1 of n2 sine theta 2 over n1. Okay, and what we'll find here is that the critical angle is 40, let's see how many sig digs we have. It looks like 3 sig digs. This is an exact number, actually. This does not affect our sig digs. So 3 sig digs, so 48.8 degrees is our critical angle from water to air. And so I recommend you guys go into a pool and actually try this out and see if you actually do get 48.8. I'd be curious. I assume it's correct based off of the knowledge and the fact that I Googled the 1.33, but try it out for yourself and see if you get an angle that's roughly 45 degrees, because that's, I mean, in the ballpark of what we're looking at. Alright, I hope this video helps you better understand reflection and refraction and Snell's law, because we're going to be looking at lenses and mirrors in the next 2 videos. I hope this video helps, and good luck.